Welcome to Unit 2, Lesson 6, Differentiability. Differentiability means can we find the derivative? If a function f of x is differentiable at x, that means that yes, there is a derivative. We should be able to calculate it or graph it. If a function f of x is not differentiable at x, that means that no, there's no derivative there. F prime of x does not exist. There's no derivative at x. When can we not have a derivative? Here is an example. F of x is equal to 5 over the square of x minus 3. Okay. What happens when x equals 3? Well, when x equals 3, if we do the calculations, we see that f of 3 is equal to 5 over 3 minus 3, which is squared, which is 5 over 0 squared, which is not defined, it's undefined. It doesn't exist. We can't divide by 0. Because it's undefined, then that means that the function f of x is not going to be not differentiable. Let's look at the graph of this function to see why that's true. So let's go to Desmos. Here is our graph of the function. We see that the graph, starting from x equals 0, and we go as x increases, we see that the graph gets larger and larger and larger, and it goes up really quickly. On the other side, starting from positive infinity, as we come down, as we move to the left, the graph is also going up really quickly. When we zoom out, we see that, hey, the graph just keeps going higher and higher. Well, let's think about what the derivative looks like. Well, the derivative has to be positive, right? It's going bigger and bigger. So the derivative is also going up higher and higher. So the derivative also looks like this. The derivative from the left side goes up to positive infinity. From the right side, this is actually this is on the right hand side. The graph is decreasing, so the slope is always negative, and it becomes more and more negative as we get close towards x equals 3. So the derivative looks like this. So what's the derivative? Well, from the left-hand side, it looks like the derivative is going up to positive infinity. From the right-hand side, it looks like the derivative is going to negative infinity. So the derivative must be undefined at x equals 3. If we go to Desmos and have Desmos draw the graph for us, here's what the graph looks like. As we predicted, it goes up to positive infinity and it goes down to negative infinity. So that means that at x equals 3, there's no derivative. In other words, f of x is not differentiable at x equals 3. Let's look at other examples of graphs in which the function is not always differentiable. Here's the second one. Here's a graph. The graph looks like a straight line. In fact, from the left, it's a straight line with a slope of 1/2. But as the graph goes, the graph just stops at x equals 3 and makes a jump. It jumps up 2 higher. And on the right hand side, it keeps going at the same slope, 0.5. When we have a jump like this is not continuous. We studied continuity a little bit in Unit 1. So this function is not continuous at x equals 3. If it's not continuous, that means it doesn't have a derivative. It's not differentiable. The derivative is not differentiable. So there's no derivative at x equals 3 again. Okay. So if finally, example 3. This time, we are continuous. At x equals 2, well, the graph is going up slowly, has a slope of 0.5, until it going from the left, so starting from negative infinity, x equals negative infinity, looking towards the right-hand side, we see that the graph goes up with a slope of 1/2 until it gets to x equals 2. At the point 2, 1, the graph is still continuous, there's no jump, but suddenly it takes a sharp turn. I'm going to call this a sharp turn. I think that's the terminology Khan Academy uses. And it's a good terminology. Sharp turn. Here the slope is 1/2. Suddenly, when x is greater than 2, the slope is actually 2, which is bigger than 1/2. When that happens, it's also not continuous. Well, sorry, that's definitely wrong. It is continuous, but it's not differentiable. So let's be careful here. The graph for this one is not differentiable at x equals 2 because the slope to the left and slope to the right are not the same. So that's what I'm calling a sharp turn. To define sharp turn more precisely using limits, I'm going to make a separate video, enrichment video, extra credit video that you can watch. But for now, I'm just going to call this a sharp turn. Whenever we have a sharp turn at x equals 2, that means the function is not differentiable at x equals 2. So let's summarize. There are really 3 ways a function is not differentiable. It's not differentiable if it has a vertical asymptote. For example, we saw in the first example, if the graph looks like this, that's a vertical asymptote. If the graph looks like this, basically if it's going straight up or straight down, it's called a vertical asymptote. Straight up or down. In other words, that means that f prime of x is positive or negative infinity. Well, if the derivative is positive or negative infinity, the derivative is undefined. We call this vertical asymptote. So wherever there's a vertical asymptote, f of x is not differentiable. Next, it's not differentiable at x if our function is not continuous. So if it's going like this, and then suddenly it makes a jump like that, or it goes like this, and then suddenly it makes a jump like that. So anytime there's a jump, not continuous, it's not differentiable. Finally, anytime it takes a sharp turn, so if it's going up and suddenly it goes straight down, or if it's going straight down really quickly and then suddenly it goes straight down really slowly, these are straight lines. That's called a sharp turn. It's not differentiable wherever there's a sharp turn, right here and here. Again, in the next video, we'll define that. Well, in the extra credit video, enrichment video, we'll define what sharp turn means more carefully. Let's look at some more examples. Khan Academy has good examples for this. So here's Khan Academy. Khan Academy gives us a graph. It asks us select all the x values for which x is not differentiable. Choose all answers that apply. So they're giving us choices. Let's check each of them individually. First one, x equals -5. All right, x equals -5. That's right here. Well, we see that the graph has a vertical asymptote. The slope is going straight up here, and it's going straight down there. So, yep, not differentiable. B, x equals -4. At x equals -4, it's not continuous. The graph makes a jump from -3 on the bottom to 3 on top. So yeah, if it's not continuous, it's not differentiable. And again, A is not differentiable because it has a vertical asymptote. Okay, C, 2 more to go. C is negative 2. If we look at the graph, at negative 2, well, it's continuous. It doesn't have a sharp turn, and it has a negative slope, but it's definitely not a vertical asymptote. It's not going straight up or straight down. So it's okay. So it's differentiable. It has the derivative at x equals negative 2. Finally, at 0, x equals 0, we see that the graph takes a sharp turn. Bam! It takes a sharp turn. The slope was definitely negative and suddenly becomes positive after x equals 0. Because it takes a sharp turn, it's not differentiable. Okay? So we can select A, B, and D. All of them are not differentiable. Let's check. Yep, that's correct. Okay. Let's look at one more example. Again, a function. Select all the x values for which g is not differentiable. At x equals negative 4, it's not continuous because it takes a jump. At x equals negative 1, that's okay. It's continuous. The slope is 0, actually, and that's okay. It's not a vertical asymptote, so it's differentiable. Also, it's continuous. C, x equals 2, well, that's actually a vertical asymptote. It's going straight up. The graph is going straight up. See, the slope, the graph is going straight up. Straight up at x equals 2. Because it's going straight up, that means that it's a vertical asymptote. It's not differentiable. Finally, at x equals 8, there's a jump. It's not continuous. Because it's not continuous, it's also not differentiable. So A, C, and D are not differentiable.